In the second part of 4.3, our section on right triangle trigonometry, we're going to talk about what are called identities and use identities to help us solve trigonomic problems without doing a bunch of extra work. Like we're able to get to the answer much quicker using these identities. Now, what I want to note to you guys is that last year you should have seen something like that that says sine squared theta plus cosine squared theta equals 1. That's called a Pythagorean identity. But before we talk about where that comes from, I want to note a couple of things about notation. If I have sine theta squared like that, that is not the same as sine squared theta. The first one, the former sine theta squared, is saying to take theta, our angle, and square it, and then take the sine of it. Whereas the second one is saying take the sine of the angle, and then square that result. Another way of writing that is if you put sine theta in parentheses and square it, that is the same as sine squared theta. The reason why we write it the other way, the way on the right, sine squared theta, is because it does get kind of tedious always writing in those parentheses every time. And it's very easy to forget that, and then you have something that means something completely different. So we want to write it this way, and it's not the same as sine theta squared. So the Pythagorean identity comes from the fact that on the unit circle, so if we have our grid here, and we have our unit circle, that the hypotenuse is 1 always, no matter what. We have a right triangle there, and we have hypotenuse is always 1. And remember, the x value goes with cosine, and the y value goes with sine. So by the Pythagorean theorem, we say x squared plus y squared equals 1. But using the trig substitution, the x values for cosine, so cosine squared theta plus sine squared theta equals 1. That is the most basic Pythagorean identity because it comes right from the Pythagorean theorem. Now there's a couple other Pythagorean identities that we are going to talk about that come from this one if you were to manipulate it. Like for example, if you were to divide both sides by cosine squared, you'd get a different identity. And it just would be more useful in other situations. So cosine squared plus sine squared equals 1 is one of the identities. Another one is tangent squared theta plus 1 is equal to secant squared theta. And then the last one, cotangent squared theta plus 1 equals cosecant squared theta. Now because because the order doesn't matter for addition, you could rewrite these in either order. Okay. This one is just switching the order of that. Switching the order of the addition here, 1 plus tangent squared theta equals secant squared theta. And then that last one can be written as 1 plus cotangent squared theta equals cosecant squared theta. And we're going to be using these a lot. And we're going to be using a lot of these as we go forward in the year. The next type of identities we're going to talk about are what are called co-function identities. And it sounds a little bit confusing, but we've already talked about these a little bit before So what we'll do is we'll have a triangle here, and since it's a right triangle, if we call this theta, then this angle up here, this acute angle, well, if we have a 90-degree angle and we have this angle here in green, well, this angle in blue has to be 90 minus my green angle, or pi over 2 minus theta. Because remember, pi over 2 is 90 degrees. So this is pi over 2 minus theta. So let's label these sides A, B, and C. So A, B, C. And now, in relation to theta, my green angle, side A is opposite. So this is opposite to theta. Side B is adjacent to theta. And the hypotenuse, letter C, is hypotenuse of theta. So let's go fill those in over here on the table to the left. So sine, remember sine is opposite over hypotenuse, so it's going to be A over C. Cosine is our adjacent over hypotenuse, so B over C. And tangent is the opposite over adjacent, so A over B. Then cosecant, remember cosecant we can rewrite as sine flipped or hypotenuse over the opposite. So that's going to be C over A. Then secant is going to be cosine flipped, so C over B. C over B. And then cotangent is going to be tangent flipped, so B over A. Okay. So now, what if we were looking at the other angle instead, that blue one, pi over 2 minus theta? Well, the hypotenuse stays the same, so this is the hypotenuse to pi over 2 minus theta, but now side A is the adjacent, so adjacent to pi over 2 minus theta, and B is now the opposite to pi over 2 minus theta. So now, if we look at the blue stuff, the blue sides, the cosine of the blue, or cosine is adjacent over hypotenuse, that's going to be A over C. So the cosine of pi over 2 minus theta is equal to A over C. And now, if we look at the sine of that, sine is the opposite over hypotenuse. It's going to be the same thing, B over C, as a cosine of our other angle. Oops, so sine of pi over 2 minus theta, which equals B over C. Because I want you to notice that when we looked at the different angle, the opposite and adjacent switched. So that means for tangent, it's going to be switched. So the cotangent is the same as the tangent. And then the cosecant is going to be the same thing as the secant of the other angle, C over A. Then the cosecant of that blue angle is going to be the same as the secant of the green one. And then the same pattern, the same pattern applies down here. So tangent of pi over 2 minus theta is B over A. And if we look back at what we did yesterday, we see that pattern. with the pi over 6 and the pi over 3 family. Well, what does 30 and 60 add to? Oh, they add to 90. So we see that this pattern applies there as well. You know, the cosine of 30 degrees is the same as the sine of 60 degrees. The tangent of 30 degrees is the same as the cotangent of 60 degrees. And that's true for any two angles that add up to 90. So no matter what, if the two angles add up to 90, this relationship is true. So if you know, we had a 40-degree angle and a 50-degree angle, we could figure out the 6 trig functions of the 50-degree angle if we knew the ones for the 40-degree angle. So we can, like I said, use this to solve some problems. So we're going to use these identities to find these values, and this is going to make it so we don't have to draw a triangle and use Pythagorean theorem. So for letter A, we have the secant of theta is equal to 5, and the tangent of theta is 2 times the square root of 6. So I just want the cosine. Well, we know that cosine is 1 over the secant of theta, so this is going to equal 1 over 5. And then for the tangent, and again, like you could draw a right triangle and do Pythagorean theorem, but these identities, these cofunction identities and Pythagorean identities allow us to get there a little bit quicker. So I want the cotangent of 90 degrees minus theta. Well, up here, we know that the tangent of theta and the cotangent of pi over 2, which is 90 degrees minus theta, are the same thing. So the cotangent of 90 degrees minus theta, that's the same thing as the tangent of theta, which we know from here is 2 times the square root of 6. So again, a lot easier than drawing out the right triangle. All right, now on the next page, we have the tangent of our angle is 5. I want the cosine of b, and I want the tangent of 90 degrees minus b. Well, the cosine, we're going to have to do a little bit of work with that. So cosine, we can use the trig identity tangent squared plus 1 equals secant squared theta, because we know secant is 1 over cosine. Well, tangent squared, well, tangent is 5, so it's going to be 5 squared plus 1 equals secant squared theta. 5 squared plus 1 is 26. So 26 equals secant squared. And when we square root both sides, we get that the secant of theta is the square root of 26. Well, now we can say that the cosine of theta is equal to 1 over the square root of 26, which we can rationalize as the square root of 26 over 26. Now that one you might say, well, I could have done the triangle quicker, and maybe you could have, but I thought that this was pretty quick as well, again, if you know those identities. Then example, part 2, the tangent of 90 degrees minus the angle. Well, we know from our cofunction identities that this is equal to the cotangent of theta. Well, cotangent is 1 over the tangent, and we know that the tangent is 5, so this is going to be 1 over 5. So this is just a new way of thinking, and it's going to be difficult at first, but we're just going to keep using those identities to solve these problems. All right, in example 2, use trig identities to transform one side of the equation into the other. Work only on one side. It's usually easier to work on the more complicated side. So what we want to do is we want the left side and the right side to say exactly the same thing. Well, in order to do that, like I said, we work on the more complicated side. We have the cosecant of theta times the tangent of theta equals secant of theta. Well, what is cosecant? Cosecant is 1 over the sine of theta. And what is the tangent? Tangent is sine, whoops, not times, is sine theta over cosine theta. And we have a sine in the numerator and sine in the denominator, so that gives us 1 over cosine of theta. And we know that 1 over cosine is the same thing as secant of theta, which is what we wanted to get in the first place. So we verified that those two things are identical. So for example, if we had a problem that gave us that, well, we can make it simpler by knowing that that is just equal to the secant of theta. Okay, we can make it simpler. Now, letter B, we have cosecant plus cotangent times cosecant minus cotangent equals 1. So let's multiply this out. Let's FOIL. Now, because these are conjugate binomials, we have a plus and a minus. We know that the middle terms are going to cancel out. So it's going to be cosecant squared theta minus cotangent squared theta on the left side. We know that cosecant, if we go back up here, cosecant is equal to 1 plus cotangent. So I'm going to make that substitution down here. Cosecant is equal to 1 plus cotangent squared theta minus the cotangent squared theta. Those two are identical. And then when we combine like terms, we have cotangent squared minus cotangent squared, which is 0. So we have 1 equals 1, which is what we wanted to have in the first place. Now letter C is a little bit difficult. So what we're going to do first is we're going to split this up into two separate fractions. So the tangent of, and I'm going to change it to theta because I don't, I'm not sure how to draw that symbol very well. So we can just make it any variable we want. Tangent theta over tangent of theta. So we have tangent over tangent, which is 1. And then I can write this as cotangent times 1 over tangent theta. Well, we know that 1 over tangent is cotangent. So it's really going to be 1 plus cotangent theta times cotangent theta. Well, cotangent times cotangent is cotangent squared. And we just used it in this last problem here. That the cosecant squared is equal to 1 plus cotangent squared. So this right here is equal to cosecant squared theta, which is what we wanted to have from the beginning. So there are multiple ways you could do these problems. A strategy would be to multiply things out, break up any fractions, and try to cancel things off as you can. All right, now the last thing we're going to do is a word problem. So we have a 25-meter line is used to tether a helium-filled balloon. Because of the breeze, the line makes an angle of approximately 75 degrees with the ground. Draw a right triangle that gives a visual representation of the problem. What is the height of the balloon? So we have a right triangle. There's the height. We know this angle is 75 degrees, and we know this is 25. So in relation to that angle, this is the opposite side, this is the hypotenuse, and this is the adjacent. So opposite and hypotenuse is sine. So we do the sine of 75 degrees is equal to the opposite side, h, over 25. Multiply both sides by 25. And again, make sure your calculator is in the correct mode. We are in degrees right now, so we're going to make sure that we have degrees. So 25 times the sine of 75 gives us 24.148. So H equals 24.15 meters. So that's it for part 2 of section 4.3. This part probably was a little bit review from the last couple years. These types of problems, it just requires us to start thinking in a different way, and looking at that and saying, what do we have, and what am I asking you to figure out, and how can we get there with the information that's given? And it is going to take time, so don't feel discouraged if you don't get it right away. So thanks for watching the video. Make sure to like it and subscribe.